Here we have a block with mass m is pushed against a spring that has a force constant of k, compressing it at a distance x from its equilibrium position. The block is then released, and the spring projects it along a frictionless horizontal surface and then up a frictionless incline of angle phi. How far up the incline does the block travel? The first step is to identify the variables that are given by the problem and by examining the figure. First we set the origin at the lowest point the block will reach. We see that it starts at the bottom y1 position of the incline and it starts at rest, and attached to it is a compressed spring with spring constant k and compression length x. The block moves along a frictionless surface for both the horizontal and inclined plane. As the block reaches the maximum height at the inclined plane, which we will set as the final position or position y2, its velocity would be 0. So at y1, we only have the potential energy due to spring, and at position y2 we only have the potential energy due to gravity. The next step is to use the ideal equation for the problem at hand. So we recall the total mechanical formula and we rewrite this as the sum of the initial potential and kinetic energies equal to the final potential and kinetic energies. We then substitute the known and unknown values to the formula and we get the value for the magnitude of velocity, or simply speed, at the second position, which is equal to the square root of 2 times g times y. To determine the distance it travels up the inclined plane, we calculate the length d as shown in the figure. We use the sine function to do this. The sine theta is equal to the height over the distance d. Rewriting this to solve for d, we get that d is equal to h over the sine of theta. We then substitute the equation for h and we get that the distance d is equal to the expression shown.